These are the core techniques that enable machines to perform tasks we consider intelligent. Each technique has a specific role, and together they help machine perceive information, make decisions, and solve problems. Let's begin with the first building block, search. Search helps a machine explore different possibilities and find the best solution to a problem. Whether it's finding the fastest route on Google Maps, selecting the best move in chess game, or helping a robot navigate through obstacles, search enables AI to choose the most suitable path. The second building block is knowledge representation. A machine cannot make intelligent decisions unless it has knowledge about the world. Knowledge representation provides a way to organize and store facts, objects, relationships, and rules so that the machine can understand and use this information effectively. Next comes reasoning. Reasoning allows the machine to analyze the knowledge it has, draw logical conclusions, answer questions, and make informed decisions instead of simply storing information. The fourth building block is planning. Planning helps a machine determine the sequence of actions required to achieve a specific goal. Rather than acting randomly, it decides what should be done first, what comes next, and what is the best path to reach the objective. Finally, we have language processing, also known as natural language processing or NLP. This enables machines to understand, interpret, and generate human language, making it possible to communicate naturally with people through chatbots, virtual assistants, translation systems, and AI assistants like ChatGPT. Together, these five building blocks work as a team. Each contribute a different capability, and when combined, they enable machines to exhibit intelligent behavior. Over the next episode, we'll explore each of these building blocks in detail. Let's begin with the first and one of the most important building blocks of classical AI, search. Search is one of the earliest and most fundamental concepts in artificial intelligence. Many AI problems can be modeled as a search problem. The goal is simple: start from the initial state, explore the available options, and reach the goal state by finding the best sequence of actions. Think about Google Maps finding the fastest route or a chess engine choosing the best move. In both cases, the AI must select the best solution from many possible alternatives. But how does it do that? Instead of trying every possibility randomly, AI uses search algorithms to systematically explore different paths and identify the most efficient solution. Now that we understand what search is, let's look at different types of search techniques used in artificial intelligence. AI search algorithms are broadly divided into four categories based on how they explore and solve problems. The first category is uninformed search, also known as blind search. These algorithms have no knowledge about where the goal is. They simply explore the search space systematically. Example includes BFS, DFS, and UCS. The second category is informed search. These algorithms use additional information called a heuristic to guide the search towards the goal more effectively. Common examples are greedy best first search and A-star search. Next is local search, where the algorithm focuses on improving the current solution instead of exploring the entire search space. Finally, we have adversarial search, which is used in competitive environments where multiple players are involved, such as chess. Popular algorithms in this category are Minimax and alpha-beta pruning. We will see each one of them in detail. Uninformed search, also called blind search. Why it is called blind search? Because the algorithm has no information about where the goal is located. It doesn't know which path is better or closer to the solution. It simply explores the available possibilities. One of the most popular uninformed search algorithm is breadth first search or BFS. BFS explores nodes level by level. It first visits all the immediate neighbors of the starting node. Only after completing one level does it move to the next level. In this example, the search starts at node A. First it explores B and C because they are directly connected to A. Next, it visits D, E, F and G, which belongs to the next level. So the transversal order becomes A, B, C, D, E, F, G. The real-world example is finding the minimum number of friends connections on LinkedIn. Suppose you want to find someone in your professional network. First, LinkedIn checks your direct friends, then it checks your friends' friends. After that, it checks the next level of connection. This is exactly how breadth first search works. It explores every level by level until it finds the desired person or reaches the goal. Another important uninformed search algorithm is depth first search (DFS). Unlike BFS, which explores nodes level by level, DFS follows a different strategy. It goes as deep as possible along one path before coming back to explore other paths. Let's understand this using tree shown here. The search starts at node A. From A, DFS chooses B. From B, it goes deeper to D. Since D has no further children, the algorithm backtracks to B and visits E. After completing exploring the left side, it returns to A and moves to the right side through C. From C, it visits F and then G. Therefore, the transversal order becomes A, B, D, E, C, F, G. A simple real-world example is exploring folders on your computer. Suppose you open the Documents folder. Inside it, you open Projects. Inside Projects, you open the AI folder. DFS keeps going deeper into one folder until there are no more subfolders. Only then does it return and explore other folders. This is exactly how depth first search works. It completely explores one path before moving to another. DFS is useful when the solution is expected to be deep inside search space, but unlike BFS, it does not always guarantee the shortest path. The third uninformed search algorithm is Uniform Cost Search or UCS. Unlike BFS and DFS, Uniform Cost Search considers the cost of traveling from one node to another. The goal is simple: choose the path with the lowest total cost. Let's understand this using the example shown here. Suppose we want to travel from node A to node C. There are two possible paths. First path is direct route from A to C, which has a cost of 8. The second path is A to B, which costs 2, and then B to C, which costs 5. At the beginning, UCS examines the available path from A. It sees A to B with cost 2 and A to C with cost 8. Since 2 is smaller than 8, UCS expands node B first. From B, it discovers another route to C with an additional cost of 5. Therefore, the total cost of the path A to B to C is equal to 2 plus 5 is equal to 7. Now UCS compares the two complete paths. A to C is 8 and A to B to C is 7. Since 7 is smaller than 8, UCS selects the path A to B to C. This becomes the optimal solution. The important idea here is that UCS does not simply look for the shortest path in terms of number of nodes. Instead, it looks for the path with the minimum total cost. This makes uniform cost search very useful in applications such as route planning, navigation systems, and network routing, where different paths may have different cost. Let's look at informed search. The algorithm has some extra knowledge or estimate about the goal. In informed search, a heuristic is a rule, estimate, or educated guess that helps the search algorithm decide which path is most promising to reach the goal. A heuristic function is usually written as h of n, where n is the current node. H of n is estimated cost or distance from node n to the goal node. The heuristic does not give the exact cost, it only provides an estimate. Real life example would be Google Maps. Suppose you are traveling from place X to Y. You have several roads. Road A 150 km remaining, road B 130 km remaining, road C 170 km remaining. The remaining distance is used as heuristic. The algorithm chooses the road with smallest estimated distance. Here h of A is equal to 150, h of B is 130 and h of C is 170. Since 130 is smallest, the search explores road B first. One popular informed search algorithm is greedy based first search. Its strategy is very simple. Always move towards the option that appear closest to the goal. Let's look at the example. We start at node S and want to reach the node G. The algorithm examines the neighboring nodes. Node A has heuristic value of 6 and node B has heuristic value of 2. Since the smallest heuristic value means the node appears closer to the goal, the algorithm chooses B because 2 is less than 6. From B, the algorithm directly moves to the goal node G. Therefore, the path selected by greedy best first search is S to B, then to G. Now let's calculate the total cost. The cost from S to B is 1. The cost from B to G is 10. So the total cost becomes 1 plus 10 is equal to 11. Notice something important here. Although B looked closer to the goal, according to heuristic value, the actual path cost turned out to be quite large. Greedy based first search only considers the estimated distance to the goal represented by h of n. It completely ignores the cost already traveled. Because of this, it may reach the goal quickly, but it does not always find the optimal path. This limitation leads us to one of the most powerful search algorithms in artificial intelligence, that is A-star search. Let's move on to A-star search, which is another informed search algorithm. The key difference is that in GBFS only considers the heuristic value h of n, meaning it chooses the node that appears closest to the goal. While this often makes it fast, it doesn't always produce the shortest or optimal path. A-star improves this by considering both the actual cost already traveled and the estimated cost remaining. It uses the formula f of n is equal to g of n plus h of n. Here g of n is the actual cost from the start node to the current node. H of n is the heuristic estimate from the current node to the goal, and f of n is the total estimated cost. Instead of choosing the node with the smallest h of n like GBFS, A-star always expands the node with the smallest f of n value. By balancing the cost already spent with the estimated cost left, A-star is able to find the optimal path when the heuristic is admissible. A practical example is Google Maps. Unlike a greedy approach that might simply head towards the destination, Google Map considers the distance already traveled, current traffic conditions, and the estimated time remaining before recommending the fastest route. Let's see how A-star search works with a simple example. We start at the start node S, where the path cost is g of s equal to 0. From S, we have two possible nodes, A and B. For node A, the actual cost is 5 and the heuristic value is 6. So the total estimated cost is f of A equal to 5 plus 6 is equal to 11. For node B, the actual cost is 1 and the heuristic value is 2. Therefore, f of B is equal to 1 plus 2 is 3. Since A star always chooses the node with the smallest f value, it expands node B first. From B, we can reach the goal G. The total actual cost through B is 1 plus 10 is equal to 11. Since the heuristic at the goal is 0, the total estimated cost is also 11. At this point, node A is still waiting in the queue with f value of 11. A star doesn't stop immediately because there could still be a better path. Next, A star expands node A. From A, we reach the goal with an actual cost of 5 plus 1 is equal to 6. Again, the heuristic of the goal is 0. So f of g via A is equal to 6. This is lower than the previous cost of 11. So A star updates the best path. So final selection path is S, A, G, total cost of 6. So far we have looked at search problems where the AI tries to find the best path or the best solution. But not all problems are like that. Sometimes the AI is not solving the problem alone. Instead, it has to compete against an opponent who is also trying to win. This type of problem is called adversarial search, also known as competitive search. The word Adversarial simply means having an opponent or rival. Think about games like chess, tic-tac-toe, or checkers. In these games, every move you make is immediately followed by the move from your opponent. So the AI cannot simply ask, "What is my best move?" Instead, it has to think one step further. It asks, "If I make this move, what is the best response my opponent can make?" Only after considering the opponent's strongest possible response does it choose its own move. This idea forms the basis of one of the most important algorithms in artificial intelligence called Minimax. The idea behind Minimax is very simple. First, the AI thinks about its best possible move. Then it predicts the opponent's best response. Finally, it chooses the move that is the safest and most beneficial, assuming the opponent will always play perfectly. Let's understand this with a real-world example. Imagine a game of chess. Before moving a piece, a chess playing AI doesn't just think about its current move, it also predicts what the opponent is likely to do next. For every possible move, it asks, "If I move here, what will my opponent do?" It repeats this through process of many possible moves before selecting the best one. This ability to look ahead and anticipate an opponent's action is what makes Minimax such a powerful algorithm in adversarial search. Let's understand the Minimax algorithm, which is used in adversarial or competitive search, especially in two-player games like chess or tic-tac-toe. In this game tree, there are two players. Max, which represents our player, tries to maximize the score. Min, the opponent, tries to minimize the score. We evaluate the tree from bottom up. First, let's look at mean node 1. It has two possible outcomes, 3 and 12. Since mean always chooses the smaller value, it selects 3. Therefore, mean node 1 returns 3. Next, we evaluate mean node 2. Its possible outcomes are 2 and 9. Again, mean picks the smaller value, which is 2. So mean node 2 returns 2. Now we move to the max node, which is the root of the tree. Max receives two values from its children, 3 and 2. Since Max always chooses the larger value, it selects 3. Therefore, the optimal decision is to choose the left branch, which generates a score of 3, assuming the opponent always plays optimally. This example demonstrates the core idea of Minimax algorithm. Max tries to maximize the minimum guaranteed payoff, while Min tries to minimize Max's advantage. At this point, you might wonder, why didn't Max choose 12 since it's the largest value? The reason is that after Max selects a branch, it becomes Min's turn. If Max goes to Min node 1, Min has two options, 3 and 12. Since Min always tries to minimize Max's score, it chooses 3, not 12. So Max cannot expect to receive 12 because it assumes the opponent plays optimally. This is the core idea of Minimax algorithm. It evaluates the tree from bottom up, where mean first chooses the smallest value and then max selects the largest among those returned values. That's why the final answer is 3, not 12. Minimax algorithm helps an AI choose the best possible move by assuming that the opponent always plays optimally. However, there is one problem. As game becomes more complex, the number of possible moves grows rapidly. For the game like chess, there are millions of possible game positions. If Minimax evaluates every single branch, it becomes very slow and computationally expensive. So the question is, can the AI avoid exploring the branches that cannot possibly change the final decision? The answer is yes, and that's exactly what alpha beta pruning does. Alpha beta pruning is an optimization technique for the Minimax algorithm. Instead of evaluating every branch of the game tree, it skips or prunes the branches that cannot affect the final outcome. Let's understand this with a simple example. Imagine you are playing chess and you have already found a move that guarantees a winning position. Now you start analyzing another possible move. Very quickly, you realize that the new move will never be better than the winning move you have already found. So does it make sense to continue analyzing every continuation of this weaker move? Of course not. Since it cannot improve your decision, you simply ignore it and focus on better options. This is exactly what alpha-beta pruning does. It intelligently skips branches that are guaranteed not to influence the final decision. As a result, the AI performs much less computation, saves time, and still arrives at the same optimal move as the Minimax algorithm. Let's understand alpha-beta pruning step by step using this game tree. Just like Minimax, we have two players. Max tries to maximize the score while Min tries to minimize it. To decide which branches can be skipped, alpha-beta pruning maintains two values throughout the search, alpha and beta. Let's first understand what these values represent. Alpha, denoted by the Greek letter A, is the best score that Max can guarantee based on the branches explored so far. Beta, denoted by B, is the best score that Min can guarantee based on the branches explored so far. At the beginning of the search, Max has not explored any branches, so it has no guaranteed score. Therefore, we initialize alpha to negative infinity. Similarly, Min has not explored any branches either, so we initialize beta to positive infinity. Now let's start evaluating the tree. We begin with the left subtree, Min node A. The first leaf node we encounter has a value of 3. Since Min always chooses the smaller value, it updates its beta value. Initially beta was positive infinity. Now we compare positive infinity and 3. The smaller value is 3, so beta becomes 3. At this point, we have only evaluated the first child of mean A. The second child with value 5 is still waiting to be evaluated. In the next step, we'll see whether evaluating that node changes anything, and then we'll continue updating the alpha value at the root. We evaluate the second leaf node which has value of 5. Remember, mean always chooses the smaller of the available values. So we compare the current beta value which is 3 with the new value 5. Mathematically we write beta equals the minimum of 3 and 5 which is 3. Since 3 is already smaller than 5, beta does not change. Therefore mean node A returns the value 3. Now we move back to the root node which is a max node. Max has now received its first result from the left branch. Until now alpha was initialized to negative infinity because Max hadn't evaluated any branch. Now Max compares negative infinity with the value 3. The larger value is 3, so alpha is updated to 3. This means that based on everything explored so far, Max can now guarantee a score of at least 3. At this stage, the root node knows one branch can produce a value of 3, while the right branch has not yet been evaluated. So the current situation is the left branch returns 3 and the right branch is still unknown. Now let's move to the right subtree, which is mean node B. Remember, after evaluating the left subtree, the root node, which is Max, has already updated its alpha value to 3. So when we visit mean B, we pass the current values. Alpha equals 3 and beta equals positive infinity. Now let's evaluate the first child of mean B. The first leap node has a value of 2. Since mean always chooses the smaller value, we update beta. We compare positive infinity and 2. The smaller value is 2, so beta becomes 2. At this point, let's look at our alpha beta values. Alpha is 3, beta is 2. Now we check the alpha beta pruning condition. The pruning rule is if alpha is greater than or equal to beta, we stop exploring the remaining branches. Let's substitute the values. Is 3 greater than equal to 2? Yes, the condition is true. But why does this mean we can stop? Think about it this way. Max has already found another branch that guarantees a score of 3. Now we are exploring a branch with mean has already shown it can force the result down to 2. Since Max always prefers the larger value, it would never choose a branch that can give at most 2 when it already has another branch guaranteeing 3. So No matter what value is hidden behind the second child, it cannot make this branch more attractive to max. Even if we evaluated the node with value 10, mean would never choose it. Remember, mean always selects a smaller value. Mean has already found 2, so it would choose 2 instead of 10. That means the value 10 can never influence the final decision. So instead of wasting time evaluating it, alpha beta pruning simply skips it. This is called pruning. By avoiding unnecessary calculations, the algorithm becomes much faster while still producing the same final result as the Minimax algorithm. And that's the final result. The optimal value is 3. Notice that we didn't need to evaluate every node in the game tree to reach this destination or decision. This is why alpha beta pruning is preferred over the basic Minimax algorithm. It finds the same optimal move while saving both time and computation. To make intelligent decisions, an AI system must first possess knowledge. Think about humans. When we answer a question or solve a problem, we rely on a knowledge we have gained through learning and experience. Artificial intelligence works in a similar way. Before an AI system can reason or make decisions, it needs information about the world. This brings us to knowledge representation. Knowledge representation is the process of storing information about the real world in a format that computer can understand and use. The place where this information is stored is called knowledge base or KB. You can think of a knowledge base as the AI system's memory. It stores three important types of information. The first is facts. Facts are statements that are known to be true. The second is rules. Rules describe logical relationships or conditions. The third is relationships, which describe how different concepts are connected. Together, these facts, rules, and relationships form the knowledge base. Now let's understand with a simple example. Suppose we are building an AI system that understands animal. First, we store some facts in the knowledge base. We know that a dog is an animal and cat is an animal. Instead of storing these facts in plain English, the AI stores them in a structured form. Now we store a rule. The rule says if X is an animal, then X can breathe. In logical notations, we write this as shown. Here X represents any animal. Now comes the interesting part. The AI already knows the fact animal dog. It also knows the rule if something is an animal then it can breathe. The AI combines these two pieces of knowledge. Since dog is an animal and all animals can breathe, that means dog can also breathe. Notice something important. Nobody explicitly told the AI that dogs can breathe. It discovered this fact on its own by applying a rule to an existing fact. The process of generating new knowledge from existing facts and rules is one of the most powerful ideas in artificial intelligence. People often use the words data, information, and knowledge interchangeably, but in artificial intelligence they have very different meaning. Let's understand the difference with a simple example. First, we have data. Data consists of raw, unorganized facts that don't convey much meaning on their own. Suppose I simply write John, 25, engineer. These are just individual pieces of data. At this stage, we don't know what they represent or how they are related. Now let's add some context. Instead of isolated values, we say John is 25 years old. John works as an engineer. Now the data has meaning. This is called information. Information is simply data that has been organized and given context, making it understandable. But artificial intelligence goes one step further. It doesn't just store information, it also stores rules and relationships. Suppose the AI already knows two things. The first piece of information is John is an engineer. The second is a rule. All engineers are professionals. Now the AI combines these two facts. It thinks if John is an engineer and all engineers are professionals, then John must also be professional. So it derives a new conclusion. John is a professional. Notice something interesting? Nobody explicitly told the AI that John is a professional. The AI figured it out by applying a rule to the information it already had. This is called knowledge. Knowledge is more than just storing facts. It is ability to use facts, rules, and relationships to derive new facts and draw logical conclusions. Let's look at reasoning. AI stores knowledge in a knowledge base. The next question is, how does the AI use the knowledge? The answer is reasoning. Reasoning is the process of applying logical rules to known facts in order to derive new conclusions. The component responsible for this is called the inference engine. Think of the inference engine as AI's reasoning engine. It examines the facts, applies the appropriate rules, and generates new knowledge. Let's understand reasoning with a simple example. Suppose our knowledge base contains the following information. The first is rule. All students who score above 90 are eligible for a scholarship. The second is a fact. Bob scored 95. Now the AI starts reasoning. First, it checks Bob's score. Since 95 is greater than 90, Bob satisfies the condition in the rule. The AI then applies the rule. Students who score above 90 are eligible for the scholarship. Therefore, it arrives at a new conclusion. Bob is eligible for the scholarship. Notice that nobody explicitly stored the statement Bob is eligible for scholarship. The AI discovered it by combining an existing fact with an existing rule. If a student X has a score Y and Y is greater than 90, then X is eligible for the scholarship. When we substitute Bob for X and 95 for Y, the rule becomes true. Therefore, the AI derives a new fact. The process of applying rules to known facts and deriving new conclusion is called inference. Inference is the mechanism that enables AI systems to reason logically and generate new knowledge from what they already know. So let's see planning. Knowing what is true is only part of intelligence. An intelligent system must also decide what to do next. That is where planning comes in. Planning is the process of determining a sequence of actions that will achieve a specific goal. Think of it this way. Reasoning answers the question, what is true? Planning answers the question, what should I do? Planning becomes especially important when a goal cannot be achieved in a single step. Instead, the AI must break the problem into a series of smaller actions. The planning process starts with the current state, which represents where the system is now. Next, a planner analyzes the available actions and determines the best sequence of steps. These steps form an action sequence which eventually leads to the goal. Let's understand this with a simple example. Suppose the goal is to reach the airport. The AI doesn't magically appear at the airport. It creates a plan. First, book a taxi, then travel to the airport, finally arrive at the airport. Each action moves the system one step closer to the goal. This ability to plan a sequence of actions allows AI systems to solve complex problems in robotics, autonomous vehicles, navigation systems, and many other real-world applications. Until now, we taught machines using rules and logic. But what if machines could learn directly from data? The idea leads us to the machine learning. In next episode, we will start exploring how machines learn patterns from data instead of being explicitly programmed. So journey ahead is machine learning, deep learning, generative AI, agentic AI. Thank you.